Good morning. Anybody have any questions or issues they wanted to address before we get into today's topic, which is Kirchoff's rules in analyzing circuits? Bella? The quiz will be on Chapter 9 content, which was what? Resistance, voltage sources, resistor networks. Well, the quiz is happening today, so I don't know. I can answer this with lots of different answers. I don't know how it's going to affect your life. So, um, okay, so I put up a question here. Can you think of a way to combine resistors or a circuit with resistors in it where you can't describe those resistors as being in parallel or being in series? Something to think about. We're going to address that situation today because it turns out there are such networks, and we need to be able to analyze circuits that have those more complicated systems in them. And we're going to use what's called Kirchoff's rules. A pair of rules. I know some of you have some familiarity with this from maybe a previous class in high school or something like that. But it's a systematic way to analyze arbitrary circuits. And so we're going to get to that. We're first going to just sort of review the way that we've been doing it, which is simplifying networks of resistors into an equivalent resistance. And the other thing we're going to do today is introduce the concept of ground in a circuit so that we can talk about the voltage at different points in the circuit rather than always talking about the voltage difference across elements. And all of this is just a way to be systematic and simplify our analysis of circuits. So up until now, the way we've been dealing with resistors in circuits is by considering the equivalent resistance when possible. So we might have a circuit that looks something like this. Here we've got an 18-volt EMF, so a voltage source. And then loading this circuit, we've got these three different resistors. And so if we want to describe what's going to happen in this circuit, we expect there to be current that's going to flow. And it's going to flow from the positive terminal, which is always this long line. So this is the symbol for a voltage source. I realized I don't think I just introduced that in class. But the long line and the short line represent a voltage source, and the long line is the positive side of that. So the left side here is at higher voltage than the right side. So current will flow from high voltage to low voltage, meaning it will flow counterclockwise around this circuit. And the amount of current that will flow depends on how much resistance we have here. But all of that current will flow through this first 4 ohm resistor. Okay, that's in series with our voltage source. So whatever comes through the voltage source has to go through that resistor. And then it's going to split at this junction, at node C. And we've done some problems where the two paths are symmetric, where there's the same resistance. And so we were able to argue just on symmetry that it should split in half. But that's not always the case. In this example, there's less resistance on the bottom than there is on the top branch. And so we might expect more of the current to go through the bottom branch than through the top. And really what we need is we need the current times the resistance, V equals IR. We need the voltage drop across this resistor to be the same as the voltage drop across that resistor, because they're in parallel and they have to have the same voltages across them. The voltage across each of them is the voltage at C minus the voltage at B. And that has to be the same. So that tells us that the I times R through this resistor equals I times R through that resistor. If they have different R's, they're going to have different I's. And so, yeah, we know that the current's going to go counterclockwise, and then we're going to get more current going through the bottom where the resistance is lower. And in fact, we're going to get twice as much current going through the bottom as goes through the top because the resistance is half as much. So if we wanted to qualitatively analyze this circuit or quantitatively analyze this circuit, we could do that by first, what would be the first step? If we wanted to calculate how much current flows in this, what's the first step in figuring that out? Find the total resistance. Yeah. So we've got 3 resistors. How are we going to combine these? What's the first? There's, so do the 2 resistors. Okay, so let's consider the 2 resistors in parallel. We would add 1 over 6 ohms plus 1 over 3 ohms, which would give us 3 over 6. And when we take the reciprocal of that, that's our 2 ohms. So this is an equivalent circuit here. And now we have these 2 resistors in series. So we can add them up to get a 6 ohm total resistance. And our 18 volts flowing through or across 6 ohms is going to result in 3 amps of current. Okay, so now we know how much current flows. And then if we want to figure out how much goes through each resistor, we can just work our way backwards. So this was the current through the total circuit, but that's also the current through this sort of intermediate circuit that we drew. And so we know there's 3 amps through each of these resistors. And so what that means is, if there's twice as much current on the bottom branch as there is on the top, it must be 2 amps through the bottom and 1 amp on the top. So we end up back at this original diagram with the current through each resistor worked out. And we can check that this is consistent because we know V equals IR. So 3 amps through 4 ohms must be a 12 volt difference. So IR is 12 volts in this case. So the difference in voltage from A to C must be 12 volts. Likewise, 2 amps times 3 ohms is 6 volts. So there's 6 volts across this resistor. And we also need 6 volts across this resistor, which is 6 ohms times 1 amp. That's also 6 volts. And then what we see is that gives us 12 volts across between A and C, and 6 volts from C to B. And so that total is 18 volts. So I go up an 18, up, whoops. I got to go through all my animations again. So on the top branch here, this voltage supply supplies 18 volts, and then on the bottom, this load reduces the voltage by 18 volts. Okay, so that those things match up. And that's sort of pointing towards the method of using Kirchoff's voltage loop, where we can say that as we go around the circuit, we're going to have some elements that increase the voltage and some that decrease the voltage. But when we go all the way around, we need to end up at the same voltage we started at. Okay, because remember, voltage is potential energy per unit charge. So if I have a charge that flows through the circuit, when it comes back to the same point, it has to have the same potential energy. Because potential energy depends on where it is. So it has to have no net voltage gain or loss around a circuit. Now, one thing that can be really useful to simplify our analysis of the circuit is to pick a reference point in the circuit to call it 0 voltage. It's equivalent to picking a point where we call the potential energy 0. In mechanics problems, we often do that. We say y equals 0 at ground level, and then we can measure potential energy based on the height above that point. And we do the same thing in circuits. We call that reference point the ground. And we use this little symbol here, these typically 3 lines in like a triangle shape. Sometimes it's just a triangle that's drawn. That is a symbol that means ground. And ground means 0 volts. So if we're free to draw that anywhere we want in the circuit. Pick any point we want as the point of 0 voltage. And then we can talk about not just the voltage across different devices or different elements. We can actually talk about the voltage at various points. And so at point B here, the voltage is going to be 0 because we've defined it as 0 by drawing in our little ground element. But we know that over here at point A, we must be 18 volts higher than at point B because we have an 18 volt voltage supply between them. And that means the voltage at A has to be 18 volts. Now we said over here that there must be a 12 volt difference between A and C based on Ohm's law and the current that we found through this 4 ohm resistor. And so the voltage at C has to be 12 volts less than the voltage at A. It's less because current is flowing from A to C, and current flows from high voltage to low voltage. So it must be going down in voltage. So 12 volts lower means the voltage at point C would be 6 volts. And then we can see that our final leg from C to B, the voltage drops by 6 volts, which is what we expected from Ohm's law and the current that we solved through these rightmost resistors. Now we could have drawn the ground over here at the left at point A, and if we had done that, what do you think the voltage at point C would have been? Would it still be 6 volts? Or would it be minus 12 volts? We need point C to be 12 volts lower than point A. So if we define point A to be ground, point C is minus 12 volts and point B is minus 18 volts. Okay, so we're just shifting our reference point, but we're not changing the voltage difference between various points. So this reference node that we call ground can just be an arbitrary point in a circuit. But sometimes it has a physical meaning. Okay, sometimes our circuit actually is physically connected to the ground, which is where that term comes from. So electrical plugs often have that third prong that is called a grounding prong or grounding pin. And if you don't have a three-pronged outlet, you might need one of these adapters. And this little tab here is what connects to the third prong. And nobody does this, but what you're meant to do, to use this safely, is to connect a wire from this prong over here to some piece of metal that goes into the ground, usually a pipe. And when I say connect a wire, we can see this green wire wrapped around. This is not where it's connected. That's mechanically connected, but the green is insulated. So the electrical wire is not actually connected to the pipe there, but up here, the wire gets stripped and is clamped onto the pipe. So the metal of the wire is making contact with the metal of the pipe. And the reason you do that is to make the ground, which is a conductor, electrically connected to a part of your circuit. Usually a part of your circuit that you're worried that somebody might touch. And if they touch it, you don't want them to get a shock. So if it's connected to the ground, then it's at the same voltage that the person is at. So they're not going to have current flowing through them. So that's why it's considered a safety device. Some circuits will have a physical connection to ground, others won't. We can use that ground symbol either way, but if our circuit does have a physical connection, that's the point we should identify as ground. Okay, questions so far? Then let's try to look at some complex combinations of resistors and identify whether they're in parallel or in series. Okay, so our rules that we're going to use is that when you have two elements in parallel, it means they have the same voltage across them. These two elements, these could be resistors, they could be capacitors. I'm just drawing them as arbitrary objects in a circuit. These are in parallel because whatever the voltage across one is has to be the same as the voltage across the other, since both sides are connected by wires and are at the same potential. Resistors are in series when they have the same current through them, when the current that flows through one has to flow through the next. So with that in mind, I would like you to consult with your neighbors and see if you can categorize each of these 12 resistor networks in terms of whether the red and the blue resistors are in parallel, series, or neither. These white resistors are present, but you're not asked about them. They're there, they have some resistance, but we only care about the red and the blue ones when we categorize them. Can you pull your mask just up over your nose? No, thanks. You guys work through all of them? Feel confident about all of them, or? Yeah. What did you think for 10 and 11? Okay. So what are you using to differentiate the two? What's the rule? Okay. So I think okay. So you're sort of using the rule that the current has to flow through both of them to be in series, and it sounds like in 10 you're arguing that that's not the case because there's a couple paths. There's two different paths that could flow. Okay, let's go through these together. Some of these were pretty straightforward. I think number one was straightforward. What is number one? Number one is parallel. How about number two? Two. I'm hearing neither for number two. I'm hearing series for number two. Someone who says series, what's your reasoning? Samar? Yeah, the same current, whatever current flows through one, has to flow through the other. So they're in series. And it might be more obvious if we straightened the wire out so that they were in a line. But what's important is that the current through one has to go through the other. So these are in series. How about number three? I hear series and I hear neither. Uh, Elizabeth, is that you? You want to explain your neither? Okay, so the voltage across the blue resistor is the voltage difference between these 2 points. But the voltage across the red resistor is between this point and that point, which is not the same thing as between that point and that point because of that additional voltage source. So that means they're not in parallel. And I think we can say they're not in series because the current that flows through one can be different than the current through the other. So in fact, those are neither series nor parallel. Yep. How about number four? That's easy. That's series. How about five? Okay, here are a bunch of neithers. We have this voltage source kind of in the way, right? We had a voltage source over here, and that made it so it wasn't parallel. Does the current through the blue resistor have to equal the current through the red resistor? What do you think? It does. So these are in series. Even though there's this voltage source between them, that doesn't change the fact that the current through one equals the current through the other. Okay, voltage sources don't give the current anywhere to go. They just take the current in one side and send it out the other side at a higher voltage. How about number six? Six looks a lot like four, which was in series, but the current now has a choice when it gets to the middle, which way it goes. So that means we don't have the same current through both resistors. Do we have the same voltage across both resistors? We don't. So one side of the resistors has the same voltage as each other, but the voltage here and the voltage there are independent. So this is neither. How about 7? First of all, are they in series? They're definitely not in series. Are they in parallel? It looks a lot like number 1, where we got these two branches. What are the rules for two objects being in parallel? Same voltage across them. So the voltage across the red resistor is the voltage difference from the left side to the right side of this circuit. Is that the voltage across the blue resistor? No, it's not, because there's also a voltage drop across the white resistor. Okay? So, for example, if there were like, let's say 6 volts there could be maybe 4 volts across this resistor and 2 volts across that resistor. And then we're comparing 4 volts to 6 volts. And those are different. So 7 is neither. How about 8? All right, is 8 in series? No, it's not in series. Are the resistors in parallel? They are in parallel because the voltage across the red one is the voltage difference between here and here. The voltage across the blue one is the difference from there to there, which is the same. So these are in parallel. How about number 9? Number 9 looks like number 8. We just removed this wire that was there. So that's neither, because certainly they're not in series, because the current through one can be different than the current through the other. But also the voltage drop across one can be different from the voltage drop across the other because of the presence of that resistor. The voltage at this point and that point don't have to be the same. Over here, they did because they were connected by a wire. But we don't have that wire present in number 9. Okay, number 10. That's neither. 11. These are in series. Whatever current flows through one has to go up through the other. And then 12. These are in series. Yeah, it's just the current through one has to equal the current through the other. And so what I sort of want you to take away from this is really applying those rules. If the current through two resistors is the same, they're in series. If the voltage across them is the same, they're in parallel. It really doesn't matter whether they're physically side by side, what you'd think of as parallel, or lined up. They don't have to be lined up to be in series. They don't have to be side by side to be in parallel. And there are cases where it's neither. All right, so there's the summary of the results is in the notes. Any questions about any of those? Any that didn't make sense after the explanation? Bella? So the white resistor is part of our voltage. There's going to be a voltage across the white resistor if there's current that flows through it. And so when we have, let's see, a circuit like this, if the resistance of that white resistor were 0, then we could say these two voltages are in parallel because there'd be no voltage across the white resistor, and so the voltage would be the same on either side. But if that resistance is not 0, and we should assume it's not 0, then there's going to be current through it and some voltage difference. So there's going to be different voltage on each side. So the white resistor does have an effect in the circuit. I was just asking about the other two. For number 9, if you take into account the white resistor, it's still neither parallel nor series. It's not both, because we don't have the same current flowing through the red and blue circuit resistors. And we don't have the same voltage across them either, because there's a voltage difference across this white resistor. And since there's a voltage difference on this side, but on this side they're at the same voltage, there must be a difference in voltage across them. So it's going to be neither. Okay, so what we were doing, whether you realized it or not, is we were, when we look at these circuits, there are points where the current can split, like this right here. We call that a junction. And if there's a junction between two elements, they're not going to be in series, because the current has an opportunity to split and go one way or the other. So it's not all going to go through the next element. And the other thing that we saw were loops like this, where the voltage across these two devices wasn't the same because of the voltage difference across that. And as we go around, the total voltage drop has to equal 0. And so if the voltage here across this is not 0, these two can't be the same. So we can go back to our simple circuit that we started with and think about this in terms of those junctions and loops. And there's two junctions in this circuit. See if you can identify where those two junctions are. There's one at point C, and there's one at point B. And by the way, points in a circuit where different wires come together are called junctions. And all the points that are at the same voltage along a wire are called a node. So like this point down to B, down to there, and up, and all the way around to there is called a node. So we can call this node B, or we can also call it junction B. And then loops. The current can travel around this upper loop, or it can travel around this lower loop, depending on which path it takes at the junction. There's also the possibility that we could have some current just swirling around this inner loop, and those are all geometric parts of the circuit, the loops and the junctions. And if we can identify the junctions and the loops in a circuit, we can come up with some equations using those to help us analyze the circuit. So there's the junction, there are the loops. There are two junctions and three loops in this circuit. And the rules that we're going to use to turn those geometric parts of the circuit into equations are called Kirchoff's junction rule, which says the current flowing into a junction, let's say through this first resistor into junction C, has to equal the current flowing out of the junction. In that case, going up through this 6 ohm resistor or down through this 3 ohm resistor. So we could write that saying the sum of all the currents flowing into a junction must equal 0. So we have some currents flowing in, some flowing out. And if the out ones are considered negative current flowing in, then all the currents flowing in must add to 0. Or just think of it as the current flowing into a junction equals the current flowing out. And then Kirchoff's loop rule says that the voltage drop around a loop must be 0. And this comes from the fact that the voltage at a point in the circuit depends on where in the circuit you are. So if you go all the way around a loop and come back to the same point, you have to be at the same voltage. So whatever voltage gains you have and then drops you have must take you back to the same voltage. So the sum of all the voltage gains around a circuit must be 0. Okay, so the way we would analyze a circuit like this using these rules would be first to label all of the independent currents that we have. So we might label the current that flows through this first resistor as I1. And we expect it to flow left to right, so let's draw an arrow left to right and give that a label I1. Don't just call it the current, don't just call it I, because we have different currents at different points in the circuit. So I1 is reasonable here. And then we have some current through the 6 ohm resistor and some other current through the 3 ohm resistor. So let's call those I2 and I3. And that's it. Those are all the unique currents I have in this circuit. There's going to be some current through this upper wire, but I don't have to draw it and label it because it's exactly the same as I1. That's all in series. Okay, and so the first rule, the junction rule, tells us that I1 must equal I2 plus I3. So we're turning this into a mathematical expression, right? We have three unknowns, the three currents. So in order to solve for all three currents, we need three equations. Here's one. The other two that we need are going to come from Kirchoff's loop rule. Now I said there's three different independent loops around there, or there's three loops around the circuit. There's the upper loop, there's the bottom loop, or there's this little circulating loop that I could draw. I can pick any two of those and draw them. So maybe I want to draw the inner loop here, just as an example. So I should draw a path around that loop. I should put an arrowhead on it so I know which direction I'm going, and I should have a clear starting point. And when I do that, I can then, as I go through the loop, every element I encounter is going to change the voltage. So I should add up all the voltage changes and add them up to 0. So when I go against the current across a resistor, I'm going from low voltage to high voltage, because current always flows from high voltage to low voltage, and I'm going against the current. So the voltage is going up. So there's a voltage gain across the 6 ohm resistor, and the voltage gain using Ohm's law must be I2 times 6 ohms. So I have plus I2 times 6 ohms as the first term in this equation. And as I continue around the loop, I find myself going in the direction of current through this 3 ohm resistor. So I'm going from high voltage to low voltage. That's a voltage drop, or a negative voltage gain. Okay, so the voltage goes down. I put a negative sign. And the amount that it goes down is I3 times 3 ohms. And that brings me back to where I started, node B. So the sum of all those voltage gains has to equal 0. And that gives me a second equation. Right, I have three unknowns, I1, I2, and I3. And now I've got two equations. I need one more. And so for one more equation, I will pick another loop and repeat this process. So if I start right here and I go counterclockwise, first I go up 18 volts as I cross this voltage source. So I have a term that looks like plus 18 volts. And then I follow the current across this 4 ohm resistor. And since I'm going with the current, there's a voltage drop of I1 times 4 ohms. And then I go through this 3 ohm resistor with the current, and it's current I3 across 3 ohms. So there's a voltage drop minus I3 times 3 ohms. And that brings me back to where I started. So those voltage changes should add up to be 0. And now I've got my third equation. If I wanted, I could draw another loop and get a fourth equation, but it's redundant. It wouldn't give me any new information. I have three equations now and three unknowns, so I can apply some algebra and solve for those. So, here's the one way to do that using substitution. And so I'm able to work out then the value for the current, I1, I2, and I3, and I can check that these match up what I found when I used simplified resistor networks. Yeah, Brianna? Okay, how did I know the direction of the current? I expect current to flow from the positive terminal of the battery to the negative terminal, which requires it go counterclockwise. Now, in this example, I can make that argument that it must flow counterclockwise. In other examples, it'd be really hard to figure out which direction current flows. You might have two different batteries in the circuit oriented differently. So what do you think would change? What if I was wrong? What if I said, I think the current's going to flow right to left, so let me draw all the currents right to left? How do you think that would affect my final results? Yeah, Vincent? They'd be negative. So all these terms, instead of being up here, instead of being negative, they'd be positive. And then when I solve for the currents, these would all be negative numbers. So whether I get a positive number to the right or a negative number to the left, in either case, that represents a current going to the right. So it's really not that important that you guess correctly. If you guess incorrectly, you'll just get a negative answer. Yeah. That's correct. This third equation does not include I2 because it's the bottom loop. And if you were to follow a charge around the bottom loop, it will never see this top resistor. It will never be part of I2. So that doesn't appear. Any other questions about how we analyze that? So the reason we want to be able to do this is because we will encounter circuits that look something like this. This is called a resistor bridge. It's actually a pretty common circuit that you have for making measurements of things. And the reason that this is needs to be analyzed using Kirchoff's rules is if you try to identify resistors that are in parallel or series, what you'll discover is that none of these resistors are in parallel or series with any other resistors in this network. So we cannot simplify this to an equivalent resistance. We can analyze this using Kirchoff's rules. So let's do that. Here's the circuit. I've drawn three loops. Well, actually, let me step back. The first step is going to be to identify the unique current. So we might call this current I1 through this top left resistor, this current I2 through the top right resistor, and let's call the current from A to B I3. Okay? Now, I could continue and call this I4 and this I5 and this I6 if I wanted to, and then use the junction rules to combine those currents or to relate them. But I can sort of do a shortcut, and I can say, well, I know that I2 and I3 flow into node B, so what flows out through this 2 ohm resistor must be I2 plus I3. So I'm basically applying Kirchoff's junction rule implicitly when I label this current here I2 plus I3. And likewise, if I1 flows into node A and I3 flows out this way, what flows out this way must be I1 minus I3. And then the current that flows through the battery over here is what gets split into I1 and I2, so it must equal I1 plus I2. Okay, so I've got 3 unique currents. If I can figure out what I1, I2, and I3 are, then I will also know what the current at every other point in this circuit is. And then next, I need to come up with 3 loops in order to solve for those 3 currents. So here are 3 loops I could consider. 1 is sort of this leftmost loop. 2 is like the outer loop. And then 3, I'll do this, this top loop here. There's also a 4th loop that I'm not considering down here around the bottom loop. I don't need to consider it because I only need 3 loops to get 3 equations to solve for my 3 unknowns. Okay, so let's set those equations up. First, around loop 1. Loop 1 is starting right here and goes, as I've drawn it, clockwise on the leftmost part of the circuit. So the first thing that I encounter is this 1 ohm resistor. So I'm going to see a voltage change as I cross over that resistor. Is the voltage going to go up or down? It's going to go down because I'm going with the current. So that's a negative I1 times 1 ohm is that resistor. And then, as I continue around the loop, I'm going to go through this 1 ohm resistor. And the current going through that one I've labeled I1 minus I3. So the voltage goes down again. So I have negative. The current is I1 minus I3, and the resistance is 1 ohm. And then finally, I go across to this voltage source. Is that a voltage drop or a voltage gain? Going from the bottom to the top. Alicia? What do you think? Is the voltage higher on the top or the bottom? It's higher on the top, so when I go from the bottom to the top, it's a voltage gain. The voltage goes up by 13 volts. And that takes me back to where I started, so I set the sum of all those voltage changes equal to 0. Now let's do loop 2. Loop 2 was the outer loop. So let me pick a starting point and then identify my loop. From this starting point, the first thing I encounter is current 2. I'm going with the current across a 1 ohm resistor. So that's a voltage drop of IR, where the current is I2, the resistance is 1 ohm. Then I go across this 2 ohm resistor, and I'm going with the current. So with the current, there's a voltage drop. The current is I2 plus I3, and the resistance is 2 ohms. And then I get over here, and I go up in voltage by 13 volts. I get back to where I start, so that has to all add up to be 0. What would change if I went around the loop in the other direction? Bella? The signs of every term would change. I'd be going against the current, so these would be voltage gains. And I'd be going from the positive to the negative terminal of the battery, so that would be a voltage drop. So you can do either one. It's not going to affect your results. And finally, let's do loop 3. So loop 3 is this one over here, where I'm first going down through the top left resistor. I have current I1 times 1 ohm. And then I go across to this middle resistor with current I3. And then I go against the current when I go counterclockwise, against current 2. So there's a voltage gain of I2 times 1 ohm. And that has to add up to be 0. Yeah, Bella? Yeah, so a voltage gain is going against current in a resistor, or from the negative to the positive terminal of a battery. Okay, so a voltage loss or a negative voltage gain is going to be the opposite of those two things. All right, so we can go through the math and solve these 3 equations for the 3 unknowns. I'm not going to go through all those steps. I'll leave that as an exercise that you can do on your own if you're interested. But what I get is I1 is 6 amps. I2 is 5 amps. And I3 is negative 1 amp. And so if I'm asked what is the current everywhere in the circuit, I know I1, I know I2. I3 was negative, which means it doesn't go left to right. It actually goes right to left. And that makes sense because, let me clean that up. If I go, let me go back to the bigger picture of the circuit. It makes sense that it goes right to left because this resistor is bigger than that one. So it's harder for current to flow this way than it is for it to flow that way. And we can imagine if this resistance was infinite, the current would have to go right to left, since it couldn't go from B to D directly. And what we have is something that's not quite to that extreme, but the same idea, that it's easier for current to flow right to left and go through this smaller resistor than to go through this big resistor. So we can make a physical argument for why that should be negative as we've drawn it. Okay, so this particular circuit is one that's called a Wheatstone bridge, or a bridge, and it's used pretty commonly for precision measurements. So imagine this circuit. I just took out the middle resistor, and what we've got is let's start with 4 identical resistors, R1, R2, R3, and R4. And let's imagine that we measure the voltage between these 2 points. Okay, well, if we put a voltage across this whole thing, and all these resistors are identical, then whatever this voltage is on the outside here, half of that must be across the top resistor and half across the bottom. So the voltage here is going to be half the total voltage, and likewise over here. But if you were to slightly change this bottom right resistor, make it a little bit larger, it's going to make the voltage here a little bit larger. If you make it a little bit smaller, it's going to make the voltage there a little bit smaller. So in essence, the voltage difference between these 2 sides can be positive or negative depending on whether the resistance of this bottom right resistor is a little bit bigger or less than the others. So it's a very sensitive way to compare resistances, just by measuring the voltage across those middle terminals. So one place you will see this is on the exercise bike at the gym that measures the amount of resistance. And the way it does that is you have this printed circuit board. This is a very close-up picture of a printed circuit board that's on an exercise bike. And you might have like a knob that you turn that like tightens a brake or changes some resistance. And the thing that's like pushing on the tire or the wheel to slow it down to provide resistance has this circuit printed on it. This is a Wheatstone bridge. There's 1, 2, 3, 4 segments that have wires zigzagging back and forth printed on this board. And a resistor is just a long, thin wire. So that's what we have here. And if we sort of color code these electrodes, we can see that the green, if current goes through the green, it gets to the center point, can either flow across this resistor and then this one to get to the white, or can flow across here and then there to get to the white. And so if we measure the voltage difference between the red and the gray, that is this center measurement in this bridge. And so what happens is if this printed circuit board gets strained because you bend it, because it's pressing up against something, it's going to stretch out a little bit. And you can see that the wires in these 2 resistors will get stretched out if you stretch this horizontally, whereas in these 2 resistors, they wouldn't, because the wires run vertically. So you're essentially changing the resistance of 2 of the resistors when you stress this board. And so by changing those 2 resistance values, it's like changing R3 and R1 here. You get a measurement of how much you've stressed this. Okay. Right. So you just measure the voltage across 2 of these pins, and that tells you how much stress there is in your board, which you relate to how much resistance there is that this board is applying to your device. Okay, let's see. Here's a problem that we can solve using Kirchoff's rules. So let's see if we can work out what voltage is necessary, V2, so that the current in resistor R2 is 0. So here are the steps. I want you to do these on your own. Label all the unique currents in this circuit. There's going to be 3 of them. So sketch out this circuit and label currents I1, I2, and I3. So hopefully you have something that looks kind of like this. Don't worry about the direction of the arrows. It doesn't matter. If you drew your directions differently than I did, you'll just get signs that are in the opposite direction for your final answer. One thing I want to encourage you to do is to use some rule for how you label things. So the current through resistor R1, I'm going to call I1. The current through resistor R2, I'm going to call I2. And the current through resistor R3, I'm going to call I3. We don't have to do that. We could call it IA, IB, IC, or I could label them in different order. But if you do it this way consistently, it makes it a lot easier to understand later on, like when you write an expression for what currents are, to know just what they represent. Okay, so that was the first step. Second one, write out each unique equation for Kirchoff's junction rule. So we've got two junctions here. Right? One junction here, one junction there. Each of them can have an equation, but I think if you write them both out, you'll find that they're the same. So why don't you write out the junction rule? So I did this at both the bottom junction, which I was calling junction A, and at the top junction, which I was calling junction B. And at the bottom junction, I had I1 flowing in, I2 and I3 flowing out, so I have I1 equals I2 plus I3. If I try to do the same thing at the top junction, I have I2 flowing in on the left, and I3 flowing in. So those add up to give me I1, which flows out. So you'll notice these two equations are redundant. They're the same. So I don't have to do both of them. So I can just write one of them. Now I want to figure out how many current loops I need to consider. So I have to take the number of unique currents, in this case 3, I've got I1, I2, and I3, minus the number of equations I've already written. So I've already said I1 equals I2 plus I3. And that leaves me with 2. I'm going to need 2 equations, so I need to draw 2 loops. So go ahead and draw 2 loops. So there's 3 possible loops you could draw. I've drawn 2 of them here in red and purple. Make sure you have arrows indicating which way you want to go around the loop, and make sure you have a clear starting point, that you don't just draw a complete circle, because I want to be able to keep track of like what is the first element I come across, so that when I write out an equation, I can look at my diagram and understand each term in the equation represents the first, second, third, fourth element that I cross in my loop. Okay, so I find and draw the necessary current loops, and now I want to write an equation for each of those loops. Okay, so I've done that up here. I had one equation for the left loop, one for the right loop. And at that point, I can go through and I can solve. Okay, so for example, from this equation for the left loop, I can solve for I1 if I assume that there's no current through R2, which is what this question was asking me about. I can set, there we go, some of these terms to 0. And what I'm left with, I can solve for current 1 from this first equation is V1 over R. And current 3 from the third equation is V2 over R2. And when I plug those back up into here, I can relate them and solve for V2, which was what I was asked. In this case, V2 has to be equal to V1 times R3 over R1 in order for no current to flow through R2. So the reason current doesn't flow through is that the voltage goes up by V2, and then when I cross R3, the current that I have, V2 over R3, times R3 gives me a voltage drop of V2. So I end up here at the same voltage that I had over here. So there's no voltage difference across R2 pushing current through it. So we can understand our result that way. Yeah. Does V2 have any effect on the current over here at junction A? Yes, in the sense that the greater V2 is, the more current will flow. And the more current that flows through here, the more current I will have here at I1 as well. Okay, so I didn't ask how much current is flowing in the circuit. I didn't ask you to find I1, I2, or I3. But the greater V2 is, the greater all those values will be. Bella? R2 is not 0, but the question asks, what is the voltage where there's no current flowing through it? So I2 is 0. For the current through resistor 2 to be 0. So we set I2 equal to 0 in these equations. So that was just from our physical constraint. Okay, so we're going to stop there and take our quiz on chapter 9. You give half of those to Sia, Joy. So you may find it helpful to use a calculator. You can use your phone as a calculator if you want.